All right, welcome back. We are still looking at magnetic circuits, and really, magnetic circuits is such a cool thing, giving us the power of circuits applied to, magnetic fields. It's such a great idea. Anyway, in this example, we've got a magnetization curve, so that's B versus H, of material X. So I just want to stop there for a second and just remind you that in a previous lecture video we were looking at silicon steel, and we had a certain curve for silicon steel. So now we have a different material X, which has a different curve, and that curve may be approximated as B equals, and then this thing here, which is a function of H, right? B versus H, where H is in amps per meter and B is in Tesla. If a magnetic circuit contains a 12 centimeter length of material X, as well as a 0.25 millimeter air gap, assume a uniform cross-section of 2.5 square centimeters and find the total magnetomotive force required to produce a flux of 10 microwebers. All right, so let's first, apply this idea of circuit analysis to this problem. I just love that. I think it's so cool. So our equivalent circuit is that we have some sort of magnetic potential. Then that magnetic potential is caused from a current carrying coil, or current carrying coils, plural. And then we've got the reluctance of the material X, so I'll just give it a subscript X, and then there's also an air gap there, and so we'll call that R gap, or script R gap, like that. So here's the circuit we're dealing with. I'm also going to label some things in my circuit as I would in an electrical circuit. I will label the potential drop, if you will, across that reluctance, and the potential drop across this reluctance. Call that X and gap, respectively. And then the neat thing here is that because it's a series circuit, I have the same flux going through all of this, right? So let's talk about those reluctances now. I've got the reluctance of the gap. The reluctance of the gap is the length of the gap divided by mu 0 times the cross-sectional area of the gap. So we're given all of that in the problem. L gap is 0.25 millimeters, and this cross-sectional area is 2.5 square centimeters, right? And then mu 0, of course, is the permeability of free space. So now what I can do is relate this to the flux using Ohm's law, essentially. So again, it's so cool. The magnetic potential across the gap is the flux times the reluctance of the gap. So that is Ohm's law applied to magnetic circuits. And so this would just be the flux times the length of the gap divided by mu 0 times the cross-sectional area. Now in our circuit, or in our magnetic situation, we should assume that the flux density B and S are parallel. Okay, we can assume that. Why is that? Well, we have these coils, presumably. Those aren't very good coils, it looks like. Anyway, and then the coils are wrapped around the material, and so that makes a magnetic flux density B, right? And then the normal to the cross section is also in that direction, right? If this is my material, so they are parallel. So I can just write, so I can use that fact, and then I can substitute just B times S in for the flux. Then, so if they're parallel, then that integral, right? The flux equals the integral of B dot ds. If they're parallel, then this is just B times S. And so that's B times S times L gap, right, over mu 0 S. All right, and so what I can do here is just I can find, well, I can rearrange this a little bit and say that B is the flux over S, okay, and then I can plug in the flux is 10 times 10 to the minus 6, mu micro is 10 to the minus 6 Weber, over the cross-sectional area. So the cross-sectional area is 2.5 times 10 to the minus 4 square centimeters is 10 to the minus 4 square meters. This would give us Tesla. So that comes out to be 0.04 Tesla from what I see there. So now I can say that I can use this relationship here that we're given in the problem, right? So 0.04 equals H. So now I'm looking at the material X, right? So actually, let me back up. So what I've done here is I've used the properties of the gap to get, you know, I've analyzed the circuit essentially using the gap. And so now I've got those properties, and so now I can back up and I can find things about the material X. So I've got 0.04 flux density now, right? I use the gap to get the flux density, and so now I can back up and use the flux density to get something about material X, that is H. So we know that they're related by that magnetization curve given in the problem. Okay, and so I need to solve this for H. So whatever you like there, a graphing calculator, or a piece of software, whatever you like, but you should get H, and I find that H is 5.1867 amps per meter. Okay, so that's the magnetic field intensity there. All right, so now I continue on with my circuit analysis, and so now I can get the magnetic potential of material X, right? And that is, since H and L, the length of the material X, are parallel, then I can just get the magnetic potential by taking H times L X. And so let me just pause there for a second and kind of take a sidestep and say, well, why are they parallel? And you can assume they're parallel because we can take the analogy from electrical circuits. In electrical circuits, the analogous situation for H would be E, the electric field, and then L, you know, some distance in the electric field. So in an electrical circuit, you know, you have some plates maybe here, and you have some plates here, and so you've got this electrical field, right? Electric field. So if I put some charge in there, right, that charge is going to move parallel to, so that the distance L is parallel to the electric field. That's exactly what's happening here. The distance Lx is always parallel to the magnetic field, and so we can just take the multiplication of those two things in a similar situation to how we did the multiplication here when those two things were parallel. So I take H, 5.1867, multiply it by the length of material X. So the length of material X contains 12 centimeters there. So I put that in meters, 0.12, and I'll come back to that, I guess, in a second. But I have Vmx and I have Vm gap, and so then I know then I can get the total magnetic potential, right? So I'll plug in numbers at the end here. So I've got the gap. This is Kirchhoff's voltage law. Vmx, like this. So this is where I'll do the plugging in of numbers. So I'll put the flux in, the length of the gap in, mu 0 s plus hx, hl times x, like that. Okay, so now this is 10 times 10 to the minus 6th times 0.25 times 10 to the minus 3, right, millimeters, over 4 pi times 10 to the minus 7 times 2.5 times 10 to the minus 4. So be careful there. Square centimeters is 10 to the minus 4 meters. And then I need to add HLX. So plus H was 5.1867 times LX. LX is 0.12, right? 12 centimeters, 0.12 meters. And I calculate that and I get 8.58 up to 3 significant digits. And what is magnetic potential measured in? Amps turns. And that is our final answer.